Hello, this is third and final part of lecture 4 of linear algebra, and this part is about linear operators. What are linear operators? Linear operators are linear transformations that take vectors in n-dimensional space and map them back to n-dimensional space. In the language of matrices, linear operators correspond to square matrices. Okay, let's consider linear operator T that takes vectors in Rn and maps them to Rn. And let's fix some bases V1, Vn of our n-dimensional space. Okay, in the first part of this lecture, we proved that linear operator T is uniquely determined by the vectors T of V1, T of V2 up to T of Vn. Okay, so what we can do now, we can take each of these n important vectors and decompose them as a linear combination of vectors V1, Vn, because V1, Vn is a basis of Rn, so they, in particular, they span Rn. Yeah, okay. So we do this for each of this vector, and we get a lot of expressions like this. Say T of Vj, it's this sum where Bij are some numbers. Okay, altogether, this gives me n square numbers. Okay, then I take these n square numbers and I put them into n times n matrix, which I called B. So what is first column of this matrix? The first column of this matrix is basically the numbers Bij, which appears in the sum when j is 1. You take T of V1, you write down this vector as a linear combination of vectors V1, Vn, you take the corresponding coefficients, and then you put it as a first column of the matrix B. Then you do the same with the second vector, T of V2, and then T of V3, and up to T of Vn. T of Vn give you the last column of this matrix. This matrix is called matrix of linear operator T with respect to the basis V1, Vn. Okay, of course, this is a generalization of what we discussed in the previous part of this lecture. If your basis V1, V2, Vn is a standard basis of your n-dimensional space, then matrix B is just a standard matrix of linear operator T. Yeah. Okay, so this is just a generalization, but of course you may ask, why do we need this? Why standard basis is not enough? Maybe it's just enough to consider only standard basis, and we don't need to worry about arbitrary basis. And then this matrix B going to be much easier to find. This is actually correct. Matrix B going to be easier to find, but in some applications, we actually have to consider special basis, because then it's going to be much easier to work with some linear operators. Let me show you one example which may convince you that in some cases it's useful to consider non-standard basis. Okay, this example is taken from tutorial 7, exercise 14. Okay, let's take this matrix A, yeah, this 3 by 3 matrix A. And using this matrix A, you can define a linear operator, which in the last part of this lecture we called by this symbol Gothic T subscript A. This is basically linear transformation from R3 to R3 given by multiplication of this matrix A. You take vector x1, x2, x3, and you multiply it by matrix A on the left, and you get back some vector in R3. Yeah, this operator going to denote by T, like in the previous slide. Yeah, and then you can notice that T of E1 is this expression, T of E2 is this expression, T of E3 is this expression. Again, you just multiply A by vector E1, and of course, if you multiply A by vector E1, you get the first column of this matrix. And when you multiply A by E2, you get second column. A by E3, you get third column. So basically, this means that this expression is equivalent to the fact that A is a standard matrix of the linear operator T, which we already know from the results of the previous part of this lecture. Okay, so basically what we did on this slide, we just repeat our construction of matrix B from the previous slide, but when V1, V2, and V3 are standard bases. And of course, in this case, as I already said, we get standard matrix of linear operator. Okay, so far so good. Yeah, but then I just say, okay, let me change the bases. Let me change different bases, not E1, E2, E3. Let me just grab 3 slightly complicated looking vectors. Okay, like this. V1, V2, and V3 are these vectors. Okay, they not much better than E1, E2, and E3, but my linear operator T, when I apply to them, you can see actually it looks a bit simpler. Okay, look, this is expression of linear operator T applied to vectors E1, E2, E3. You see it's kind of complicated. But for V1, V2, V3, the corresponding expressions are much simpler. T of V1 is minus V1. How to check it? Okay, you know that T of V1 is just A times V1. You take this matrix A, multiply by this vector V, and you observe then the result is nothing but you just change the sign of V1. And with vectors V2 and V3, it's even simpler. You multiply A by V2 and you get back V2. And you take matrix A and multiply by V3 and you get V3. So this is definitely simpler. In particular, which we're going to see a little bit later on the next slide, the standard and non-standard matrix of your linear operator T with respect to this basis V1, V2, V3, it's diagonal matrix with entries -1, 1, and 1. Yeah, it just follows from our definition. If you compute the matrix B for these vectors V1, V2, and V3, then this is going to be diagonal matrix. -1, -1, 1 on diagonal, 0 everywhere else. So matrix B is much simpler than matrix A. On the other hand, there's a price to pay. Your vectors V1, V2, and V3 are more complicated than the vectors E1, E2, E3. Okay, so let me show you how basically one can express, one can apply this fact in some case. So namely, let's take some vector x in R3. And we know that we can decompose this vector as a sum of linear combination of standard vectors. And then you got x1 times e1 plus x2 times e2 plus x3 times e3, where x1, x2, x3 are just coordinates of vector x. Or we can express it as a linear combination of vectors v1, v2, v3 in this way. Yeah, lambda 1 v1 plus lambda 2 v2 plus lambda 3 v3. Okay, we can do this. So every vector in x can be decomposed like this. And then let's just apply t to x. How to do this? Of course, we can just take matrix A and multiply by vector x. But maybe we can use the qualities on the previous slide. We know that t of x is t of this sum, but t is a linear operator. So it's the same as lambda 1 times t of v1 plus lambda 2 times t of v2 plus lambda 3 times t of v3. But t of v1 is just minus v1. You get this. T of v2 is just v2, you get this. T of v3 is just v3, you get this. So you see t of x, it's very easy to compute if you know this decomposition. And we know that such decomposition exists because v1, v2, and v3 form a basis of the n-dimensional space. So every vector is in R3 is the linear combination. Okay, good. So we have this. This already should basically give you the idea that sometimes maybe we need to choose a special non-standard basis of our vector space R3. So then we can apply this our linear operator in this new basis in an easier way. Yeah, and as I already mentioned, the standard matrix of T is complicated by the matrix of T with respect to basis V1, V2, and V3. It's extremely simple. It's just diagonal with entries -1, 1, 1 on diagonal. Okay. And of course, it's natural question to ask here how the matrix A and B are related. A is a standard matrix of your linear operator. B is matrix of your linear operator with respect some basis I choose on the previous slide. Okay, to answer this question, we can do the following. We can decompose coordinates of vector x in terms of coordinate of vectors v1, v2, and v3, and this numbers lambda 1, lambda 2, lambda 3. Yeah, and you get this expression. So basically, you substitute here coordinates of vector v1, v2, and v3. You add these vectors, and then you get these three numbers, and they correspond to the coordinates of vector x1, x2, x3. Yeah. So look, x1, x2, and x3 are coordinates of vector x. Sometimes people add in standard basis, but usually it's assumed. But these numbers lambda 1, lambda 2, lambda 3 can be considered as coordinate of vector x in the basis v1, v2, and v3. Oh, you can say with respect to the basis v1, v2, and v3. So basically, this gives you a relation between coordinates of vector x in the standard basis and in the basis v1, v2, and v3. Yeah, we can translate this equality into the matrix form. Yeah, like this. This is the same equality as before, but we have equality of coordinates. Now we just rewrote it in the matrix form. Yeah, and since we already know how to multiply matrices, how to find the inverse of matrices, if you find the inverse of this matrix and multiply this by inverse on the left-hand side, you get expression of lambda 1, lambda 2, lambda 3 in terms of x1, x2, and x3. Yeah. And one can notice that this matrix we got here has an inverse. It's invertible. Yeah. Okay, so we call this matrix M, and usually this matrix M is called change of basis matrix. Okay. Observe that its columns are just vectors v1, v2, and v3. Yeah, this is exactly how we got this matrix. Okay, and now, as I said, we can express lambda 1, lambda 2, lambda 3 in terms of x1, x2, x3 if we know how to find inverse of our matrix M, but we know how to do this. We actually know at least two ways how to find inverses of 3 by 3 matrix. We have rather complicated formula involving determinants, or we can use elementary row operations described last week. Okay, good. So we have this expression as well. And then you can compute explicitly that your matrix A is a product of matrix B times matrix M times matrix B times matrix inverse of M. You just take these three matrices. This is your matrix B, this is your matrix M on the left, and matrix inverse of M on the right. You multiply and you check that you get this. Of course, this is not a coincidence. Of course, this is a theorem, which we're going to see soon. But before we describe this theorem, let me show you how we can use this equality. And because I'm not yet convinced that I convince you that using a different basis may be useful. But let me give you one example, which probably may convince you that this equality may be useful, and using the different special basis of our n-dimensional space can be useful and helpful when we work with linear operators. Okay, observe that if we want to compute power of matrix A and we want to use this equality, this is actually can be done in a relatively simple way. Look, if you take a to the n, this is nth power of this matrix, but nth power of this matrix is a shortcut to the product of this matrix n times. So we write these matrices like this n times. This is a big product. And then we observe if we can remove brackets because multiplication is associative for matrices. So you get rid of brackets here, and then you see that every time when you see M inverse in the middle of this product, its neighbor is M. So m times m inverse, it's identity. So this product simplifies like this. And if it simplifies like this is just m times power of b times inverse of m. But power of b is very easy to compute. Yeah, because it's diagonal matrix. When you multiply diagonal matrices, you multiply the corresponding diagonal elements. And diagonal elements of B are just -1, 1, 1. So it's very easy to compute. If basically B to the power of n is identity if n is even, and it's B if n is odd. So you get this expression for a to the power of n. And if you wish, you can simplify it like this. You get this a bit complicated matrix, but this is not very complicated. Basically, this is just two matrices. When n is even, you just get identity. Yeah, if n is even, this is 1, this is identity, this is m inverse. So a to the n is 1, identity matrix, if n is even. And when n is odd, this is just -1. And then you can basically simplify this matrix a lot. I just didn't have space to do this. Okay, good. So this shows you one application of our approach. And actually, to compute the power of matrices, we need this quite often in some problems, for example, in applied mathematics. You can take a look, Fool's book, and there's several applications of matrices when you compute the power of matrices to some real life problems. So this is actually can be quite handy. Okay, so now let's go to the theorem which we can derive using this equality. So this equality is not just coincidence, it's a theorem which holds for in all possible cases. Yeah. Okay, to state the theorem, we fix linear operator that takes elements in n-dimensional space, maps into n-dimensional space. We call this operator T. As before, we fix the basis of n-dimensional space, V1 up to Vn. We denote by A standard matrix of operator T. We denote by B the matrix of T with respect to this new basis V1 up to Vn. And we denote by M the change of matrix basis. This is a matrix with columns V1, Vn. Yeah, just take this basis vectors V1, Vn, and you put them as a column of a square n times n matrix. And we call this matrix n. And then these matrices are related by these two equalities. So A is m times b times inverse of m, or b is equal to inverse of m times a times m. Of course, these two equalities are equivalent. If you know this equality, then you can express b in this equality and you get this equality. So if you want to prove the theorem, it's enough to prove one of them. Yeah, so let's give you a very, very, very sketchy idea how to prove this equality. Basically, to prove this equality, you can multiply everything by m on the right. So you get am equal mb. This is what you want to prove. So you want to prove that a times m is the same as m times b. Yeah. To do this, we can use the following proof. It's very sketchy. For the details of the proof, please take a look in the lecture notes or in the book. Or you can find the proof basically everywhere. You can take a look on Wikipedia. There's a lot of proofs of this fact. This is a standard result in linear algebra. Yeah, okay, this looks a bit scary, but let me explain what you do. You take the vector vk, yeah, some vector vk, and you accurately apply to this vector vk linear operator t, yeah, and you can proceed in two different ways. First, basically by our definition, t of vk is just this expression. This is how we define these numbers b, I, j on the first slide, but here these numbers are b, I, k. Yeah, you write it down this, but then you decompose all this, every vector vi as a linear combinations of standard vectors e1, e2 up to en. Yeah, and here mji, this is entries of the matrix M. Yeah, so every vector v1, v2, vn can be decomposed as a linear combinations of standard vectors e1, e2 up to en. It's just coordinates of vector v1. So we have this. So mji are coordinates of are entries of matrix M, because matrix M is a matrix with columns v1, vn. So you have this equality. And then, as usual, we use this change of summation trick. You change of summation, you play around, and you observe that this is nothing but the formula for the product of matrices MB. It's JK entry. Yeah, and you get this equality. Yeah, you get this equality. On the other hand, you can proceed in a different way. You can actually express this vk here in our original vector vk in terms of vectors e1, en before we apply our operator t, like this. Yeah. So we do the same thing we did here, but before applying t. And then you get this. And then you apply t, and you use the fact that t is linear. So you have this sum. And now, by definition, you know that t, when you apply to ei, you can express as this sum, this linear combination, basically where AJI are entries of the matrix A. Yeah, it's a standard matrix. This expression is equivalent to the fact that A is a standard matrix of linear operator T. So you get this sum. And then you again apply change of basis trick. Yeah, change of summation trick. You change your summations, you get this, and eventually you get this. Yeah, and then you see, okay, look. On the left-hand side, you have some vector. And on the right-hand side, you have some vector. And basically, these numbers, M, B, and these numbers, this is JK entry of the matrix MB here, and JK entry of the matrix AB. These are just a coordinate of these vectors in the standard basis, just the usual coordinates. So two vectors are equal if and only if its coordinates are equal. So we conclude that if these two vectors equal to each other, then this number is the same as this number. But these numbers are JK entries of matrices AM and MB. So we proved this equality. Okay, it's a bit sketchy, but it's very straightforward. For detailed proof, please take a look on the lecture notes. Yeah. Okay, let's consider some a little bit more simple example than we already considered before. We considered 3 by 3 example. Let's now consider 2 by 2. You take two vectors in R2, V1 and V2. V1 is 3, 1, and V2 is 7, 4. And it follows from the theorem proved in the first part of this lecture, then there exists linear operator, and it's unique, such that T of V1 is 2V1 and T of V2 is minus V2. Yeah, I just basically grab these numbers randomly, but we know that such linear operator exists, and we know that such linear operator unique because V1 and V2 are linear independent, so they form a basis of R2. Okay, and then with respect to this basis, V1, V2, matrix of my linear operator is very simple. It's diagonal, again, because this is how my linear operator basically looks in this basis. When you apply to V1, it just scale V1. When you apply to V2, it's also scale V2 by minus 1. So this means that my my matrix of my linear operator with respect to this basis is just diagonal. And the diagonal entries is exactly the scaling factors. Yeah. Okay, but now we can use the theorem on the previous slide, and we can find standard matrix of my linear operator T. How? We create a change of basis matrix M. We basically put these vectors V1, V2 as columns. We get 3, 1, 7, 4. We find its inverse. This is not very complicated. We have explicit formula for the inverse of 2 by 2 matrix in the lecture notes, and it was actually also used in the tutorial problem and in the first week, in the lectures of the first week. Yeah, so we just find m inverse of m. We multiply m times b times inverse of m, and this has to be your matrix A. Matrix A is a standard matrix of linear operator T. Yeah, and you get this matrix. Yeah, you see, it's not very nice matrix, but I mean, it's written on the standard basis. Okay, good. So using this change of matrices, A and M, B, inverse of A, this basically equality can be used to define what is called similarity for matrices. If you see matrices that equal like this, if one matrix can be obtained from another by multiplying by some matrix M and its inverse on the left and on the right, we're going to call such matrices similar. This is basically a definition. It's relatively standard. We're going to use this definition, this notation in this course, and I think it's pretty standard. Two n times n matrices are said to be similar if one can be obtained from another using this formula for some invertible matrix M. Yeah, similar matrices share a lot of common properties. Yeah, we will see this later. And basically, example on the previous slide tells me that this matrix 2, 0, 0, minus 1, it's similar to this matrix. But so now there are no linear operators. This is just, we're just playing with matrices. So we have this matrix B and this matrix A, and we already found some matrix M such that A is equal M times B times inverse of M. Invertible matrix M. Yeah. So, but you see, this matrix is diagonal. It's much simpler than this matrix. This matrix is quite complicated. Yeah. So, for example, as already mentioned, if we want to find powers of B, it's easy. If we want to find powers of this matrix, it's complicated. But using this relation, and if we found matrix M, which we did on the previous slide, then we can easily find the powers of A, any powers of A to the n. We just write down the formula like we did with the 3 by 3 matrix. Okay, and what we did with 3 by 3 matrix can be restated in this notation, that this matrix from the exercise 14 and tutorial number 7, it's equivalent to this diagonal matrix with very simple diagonal entries. Okay, so as I already said, similar matrices share a lot of common properties. In particular, their determinants are the same. If I take, in this definition, determinant of A, it's the same as determinant of B. Why? Because determinant of A is determinant of this matrix. But we know the determinant of a product is product of determinant. So this is determinant of M times determinant of B times determinant of inverse of M. But we also know the determinant of inverse of M, it's inverse of determinant of M. So determinant of M and determinant of inverse of M cancel, and we get determinant of B. So similar matrices have the same determinants. We can use this to define determinant of a linear operator. Okay, this is basically part of our big plan to translate a lot of things from the world of matrices to the world of linear operators. We translated everything in the previous part of this lecture, except determinants. Now we did this with determinants. How? So we already know that matrices with respect to all different bases, matrices of linear operator with respect to all possible bases of n-dimensional space are similar. So we can take, and we also know that similar matrices have same determinant. So it basically means if you have a linear operator, you take any basis which you like, you write down the matrix of this linear operator with respect to this basis and compute its determinant. It can be standard basis, it can be any other basis. The determinant going to be the same. Yeah. Because as I already mentioned, and I sketched the proof of this lemma, similar matrices have similar determinant. Yeah. Okay. Here is an example. So for example, if you take a look on this matrix and on this matrix and ask yourself which determinant is easier to compute, of course, it's easy to compute determinant of this matrix. It's just diagonal matrix. Its determinant is a product of diagonal elements. So this is just 2 times minus 1 minus 2. But you can check that this is determinant of this matrix as well by this lemma. So again, we can consider this number, in this case minus 2, as determinant of linear operator. Yeah. Okay. And if you taken accelerated proofs and problem solving, maybe you already covered what is called equivalence relations. If you don't, this is okay. Basically, let me just mention briefly that similarity of matrices can be used to define what is called similar equivalence relation on this set of all n times n matrices. So what this means? Equivalence relation is a relation on a set which satisfies these 3 properties. A equivalent to A. If A equivalent to B, then B equivalent to A. If A equivalent to B and B equivalent to C, then A equivalent to C. You can check that this is true for n times n matrices. So here, the sign means similarity of matrices. It's also used in proofs and problem solving or accelerated proofs and problem solving for any equivalence relation. So if you don't know what's equivalence relation, don't worry. You just look at these 3 properties. If you have A, B, C, n times n matrices, then A is similar to A. Here, this sign here in this slide is assumed to be similarity of matrices. Then if A is similar to B, then B is similar to A. And if A is similar to B and B is similar to C, then A is similar to C. Yeah. You can prove this basically using definition of what is similar. Yeah. And then that basically means that you can slice your set of all n times n matrices by like big slices consisting of similar matrices. And these slices do not overlap. And the slices usually called equivalence classes for this equivalence relation. If you already learn about this in the accelerated proofs and problem solving. If you didn't, just forget about this. And let me just consider one example. You take 2 by 2 matrices and you define, this is what's called equivalence class. Let's denote it like this, class of A. For every given matrix A, this class consists of all matrices, 2 by 2 matrices, which are similar to A. So this is basically a bunch of matrices, yeah? And this is called equivalence class of matrix A with respect to this equivalent relation. So in particular, what I mentioned, that we can slice our set of matrices into this non-overlapping slices implies that these classes are slices when you slice our matrices. So these 2 classes, either they coincide or they don't overlap, don't intersect. They're either disjoint or they're the same. Okay, this follows immediately from this, yeah, because of this transitivity property. So either they coincide or they disjoint, yeah. And for example, you can prove almost by definition that if you have identity matrix or if you have matrix identity times lambda, such matrices are called scalar matrices, then its class basically consists of only, its equivalence class consists of only identity matrix multiplied by this lambda. So if you have matrix like this, its class, equivalence class consists of 1 matrix. Okay, how to prove this? Basically by definition, if A is equivalent to lambda times identity, then there exists invertible matrix M such that A is M times lambda times identity times inverse of M, but lambda, multiplication by lambda commutes with multiplication by matrices, so you can put lambda outside, and then identity multiplied by M is M, and then M times inverse of m cancel becomes identity. So you prove that A is equal lambda times identity. This is very handy. Okay, if this looks a bit too abstract, you don't need to worry about this. We're not going to use similar matrices a lot, but it's worth to know what they are. And it's also quite important for the future to know what equivalence relations is, but you will learn it in accelerated proofs and problem solving, or maybe in fundamentals of math next semester. Okay, let me stop here.